on this very telescope here, which was constructed between 1967 and 1971. In May 1971, on May 12 actually, so 3 days ago, we had our inauguration, and well, it took us about 1 more year to say install everything properly, test everything, and so on. And since August 1972, we are doing regular observations with this telescope. The Institute nowadays has obviously many more interests and telescopes to be used. That is, as you probably know, we are the Apex telescope in Chile, in the Atacama Desert, and the Meerkat, or we are involved in the SK Meerkat prototype or development, and also run this SKA NPI prototype telescope in South Africa. But still, the 100-meter telescope is still heavily used for observations from people of our institute, but also from scientists all over the world, and many observations are also done within the VLBI network. Well, still the second largest fully steerable radio telescope in the world after the Max-Planck telescope in West Virginia, so people are interested to use that, especially in the ferrometric context. Well, actually, you see the map here on the wall. This is a somewhat arbitrary collection of radio telescopes all over the world. It's not complete and in no sense, but well, we got the ones, mostly the ones with which we were working together. Well, obviously, Effelsberg is the red marker. The black ones in Europe, these are antennas belonging to the European VLBI network, with whom we regularly do observations. The gray ones in the US, this is from the very long baseline array from the NRAO. They have their own VLBI network, so to say, but still they also very often observe together with us because of the long baseline and the high sensitivity we can provide. And then there are quite a number of other telescopes, certainly Apex, ALMA, the SKA site in South Africa, and so on. As I said, the choice is a bit arbitrary. Remarkable is maybe the antenna on the upper right. This is a satellite dish. You might know that this was a 10-meter radio telescope in the Earth orbit, in a very elliptical Earth orbit, and that was also used for VLBI. So it was a nice project to extend VLBI beyond the limits of the Earth. Well, it was a Russian project, and apart from the fact that the satellite died after some time, nowadays it's a bit difficult, obviously, to work together, unfortunately, with the colleagues in Russia. But that was a really very successful project. Okay, well, as I said, don't hesitate to interrupt me whenever you have a question, and I think we proceed now to the control room and then to the telescope.
Ну, в общем, ротана здесь нет на карте. Пихо.
Actually, we have some evidence today that's reached by the telescope currently. It's not moving, but we will soon start the program for tonight. We have, as other observatories, a 24/7 operation here, so there's always a telescope operator, currently Mr. Kiski, who started at 2 and will stay here till 10, and then comes the night shift till 6 in the morning, and the next one, and so on and so on. So, as I said, a 24/7 operation, and well, about 360 days per year. Only on Christmas and New Year's Eve we close down for a few days to give everybody some kind of rest. And as I said, normally during daytime, especially in summer, we go and do maintenance with the telescope, while at night and weekend, and very often also in winter during the daytime we observe with the telescope. Our efficiency is about 75% or so, roughly. Yeah? So that this is the fraction of the total time per year which we use for observations. Well, here to the right is more or less the place of the astronomer. Well, if he or she is here in person, which is now rarely the case. You see this middle window or this middle monitor. This is the most important monitor. There's a GUI where you can control the antenna. You choose the receiver, you choose the object you want to observe and the observing mode. And to the right is the online photo, which gives you just the first idea of what you just have observed. As I said, nowadays we don't see observers that often. During my time when I made my PhD, I spent lots of nights here at this desk. Nowadays it's far easier. First of all, this is a VNC, so the correct password you can get it wherever you are and observe from home or your home institute, whatever. And secondly, it's possible to put all observations in a queue and just keep it running, and then the operator just has an eye and looking whether there is some problem or not. The blue one, the blue screen in the middle, is the main control monitor, which gives you the most important information in one glance. This is sidereal time, the UTC, for example, the source name, the coordinates of the source in the horizontal system. You see this curve. This is changing all the time when you do real observations. You see also the source coordinates in an equatorial system, the frequency, and some weather information and so on. So this is really what you get in first, on one glance, all the most important information. And more to the left is the place where the operator can handle the telescope and check things. Especially on the very left side, this is where you can drive the telescope manually into, for example, maintenance position like now. So one position would be just pointing up towards the zenith so that everybody can go into the dish. Or you point the telescope towards the horizon and then you can easily enter the prime focus cabin. There are actually two ways to enter the prime focus. In the position as now, you have to go 30 meters via stairs, and therefore people are somewhat lazy sometimes, and they have to work at the focus cabin. They ask the operator to tilt the telescope to 7 degrees, walk into the focus cabin, and then are tilted upwards to do their work. It's an interesting experience. So you have a closed room, and then you're tilted by 90 degrees, so someone's standing there, and without outside reference. So that's quite interesting. Experience. Well, as I said, this is the online portal gives you some information about observations you do, and let me have a look whether I find something. This is the very first, so more or less the raw data, and what you see here is the very easiest observations we can do, but something we do all the time. This is a so-called cross scan. We do it every now and then, and especially at the beginning observation, to check whether the antenna is positioned correctly. So what we are doing is we drive the antenna in azimuth and elevation over one like sources, mostly some AGN far away, and then we get this kind of result. And if the maximum of the Gaussian is in the middle, then we know the antenna is well aligned, well positioned, and we can start, say, our real observations. The Gaussian curve, what you see is in principle, or mathematically speaking, the convolution of the telescope beam with the source. And the source, as I said, is point-like, so it's a delta function, and that's the reason why in principle you see the telescope beam. If the source would be extended, it would look quite different, obviously, but that would mean you haven't chosen a very suitable source for your observation. Apart from that, you could in principle have an idea of the strength of the source, just the amplitude of the Gaussian, of the system temperature, baselines, and so on. So it gives you quite some information. And as I said, this is done every now and then to check the system status.
Does it drift a lot?
Sorry?
Does it drift a lot?
Well, it depends obviously on the frequency. We usually reach, say, a pointing accuracy of about 2 to 3 arcseconds in principle. But this is only true under very good weather conditions. If it's getting windy, obviously the telescope moves. If the sun shines on the telescope, there's a lot of thermal deformation. And it makes sense, especially if you observe at higher frequencies. With higher, I mean, say, above 10 gigahertz or so. It makes sense to regularly repeat these observations. At 21 centimeter, well, the beam is about 10 minutes wide, but normally you do it every few hours or once when you start, and that's it. This is good enough. As I said, frequencies here range from 300 megahertz to 90 gigahertz. We have receivers for all these frequencies, not continuously but loosely, which means we observe wavelengths from 1 meter down to 3.5 millimeters, and that corresponds to telescope beams from something like 35 minutes or so down to 10 arc seconds at the highest frequency. And then things got really a bit more complicated, especially since, well, this was never meant to be a millimeter side. We are about 2,000 meters too low in elevation here. It works, but the telescope originally was designed to work up to 3 centimeter or down to 3 centimeter wavelengths, maybe to 1.3 K band, because there are a number of interesting spectral lines in that band. But now we are doing regularly 7 millimeter and 3 millimeter VLBI observations, and that also still works.
And the optical quality for those, for when you go for those 3 millimeters?
Well, the important parameter is obviously the RMS of the dish, of the surface, right? And this is about 0.55 millimeter in the best case. I come to that when we go a bit higher. I'll tell you a few more things about that, because this is obviously an important part of the telescope, or important property of the telescope. As I said, the telescope was originally never meant to observe up to, down to 3 millimeter wavelengths, but it works. But then the efficiency is, well, it's something like 10% or so only. Actually, even a bit less. But it's still, with 100 meters, it's still okay.
How fast does it move?
Well, we will probably see it because while you are here, we will start observation and you will see it. We can turn the telescope at about 30 degrees per minute, which means we have 15 minutes for a full circle, and 5 minutes for a turn of nearly 90 degrees. You will see that when we are down there and the telescope starts moving, this is quite fast. Well, on the other hand, I can also tell you as astronomer, as observer, and if you are here waiting for the telescope to use the source, you wish it would be faster, obviously. But on the other hand, we move 3,200 tons, and we have to do it with a certain accuracy, and that's the main part. 3,200 tons. Okay, well then, let's get a bit closer.
Спускаемся на стенку. Вот телескоп. Бункер.
So the size can be changed if they are too narrow or too wider, right? Try this one again. It should, well, not be too tight, but it should also be okay if you bend forward. So the worst thing is that the helmet falls off the telescope and hits somebody. In 5 minutes from zenith down to 8 degrees above the horizon. We can't go lower than 8 degrees, but if you look around, you see that wouldn't make much sense. We don't want to observe the trees, but the sky. But that brings up the question, why is the telescope here? Why is it located in a valley and not as any other proper telescope on a hill? And the reason is, in principle, well, it's protection against interference. There is a predecessor to this telescope. This is a Stocker telescope. It's about 10 kilometers from here or so. Also belongs to Bad Münstereifel and was the first big German radio telescope built in the mid-1950s. A 25-meter dish that was at that time really big, or actually still big. And even in the 50s and 60s, when the Stocker telescope was operated, people noted the problem with man-made radio radiation, which is obviously far stronger than everything we receive from the universe. And for example, there is a direct line of sight from the Stocker telescope to the military airport, about 10 kilometers or so away. And therefore, when this telescope was planned, the decision was made, we make a kind of a trade-off. We give up a bit of the sky, but have at least some protection against interference. And therefore, we choose this valley. Well, nowadays it's quite difficult. You have so many satellites flying around, for example, and even here in the valley you would have quite good mobile phone reception. But still, it's still better as if we were on an, let's say, more higher place. So the idea was to have a valley, and the valley should be open towards the south. South is there, and the reason is obviously astronomically. Everything which is very low in elevation at our latitudes, most prominent the galactic center, obviously, or the double pulsar or whatever, name it. Everything which is quite low, we can see it at least 2 hours or per day over the southern horizon. So that gives us a declination limit of about minus 31 point something degrees, so that we at least can see them. So that was the point why we wanted to have a north-south valley. That we were finally ended up here is, as so often, political. Money for the telescope came from the Volkswagen Foundation, you know, the German car company. But a small amount came from the government of the federal state of Germany. We are in North Rhine-Westphalia. And the government said, I think actually they purchased the ground. The government said, well, if we give you money, you stay within our state, obviously. And we are quite close. If you look on a map, you will see these hills over there are Rhineland-Palatinate, this is the next federal state of Germany. And there's a small creek running on the edge of the valley which marks the border between those states. Actually, that was one of the 2 creeks we have. The other one comes down here, which made a lot of trouble 3 years ago. You guess you were aware of this flooding catastrophe in July 2021. It also hit us. Fortunately, not the 100-meter telescope, but the whole lower part of the observatory was underwater, especially part of the LOFA field, of the LOFA telescope, especially the low-band antennas. So you can see, by the way, our LOFA antennas there. So in the front, the low-band antennas for 20 to 80 megahertz, in the back side, the high-band antennas for 120 to 240 megahertz. Well, I guess you are familiar with that, so I don't have to say much about it, I assume. The interesting story is just on LOFA. As I said, the creek down there marks the border between North Rhine-Westphalia and Rhineland-Palatinate. 50 years ago, it went right through the middle of the valley. But since this space was needed to reconstruct part of the telescope, which was then lifted up by a crane, the creek was moved towards the edge of the valley, but not the border of the estate. So actually, our LOFA is in both states. And we noted that when we asked for permission to build it, because we had to write every application twice. Okay, well, coming back to the 100-meter, we have these 2 gears here and the 4 engines. And there's actually an interesting story on these big gears. Well, I should say these are still among the few parts, except for the main structure, which are still original. So 15 years old. Most of the telescope, except for the main structure, have been replaced in the last decades, and we renewed what we could, or every time. And so there was a lot of effort, a lot of money spent to keep the telescope as modern as possible. And despite its age, it's still in a very, very good shape. Or actually, we used to say it's in the best shape ever. But these are still original. And the story about that is that the original design hadn't 2 but 4 of these gears. So there was another one here and on the other side. That's the reason why this platform is so huge, which is now quite handy for tourists. The problem is that with the second gear on each side, the telescope started to vibrate when positioned. And that was in the very early days of the telescope was a big problem. And a few years ago I found a very nasty article
in a German news magazine from 1972 about the institute and the stupid astronomers building a 30 million mark telescope which doesn't work properly. But then some clever engineer said these gears are so over-designed, just remove the outer two, you don't need them. And people did that, and since then it works fine. And the nice thing is we have spares now. And actually at some point we replaced it already for some maintenance, and that's the reason why we still can lift it, this original gear. Quite a lot. Well, actually it is quite a lot, but compared to other telescopes it's not so much, interestingly. If you compare with other existing telescopes, like say the Donald Bank telescope in Manchester, I think it is nearly twice as heavy. The Green Bank telescope is twice as heavy, and even the Sardinia telescope, which has just 64 meters of diameter, is much heavier than ours. And actually there is, this has some background obviously. I mean, the big question when the telescope was constructed was really about the optical behavior, about the optical properties. I mean, the tilting part alone weighs nearly 1,900 tons. And the question was, what do you do against gravitational deformation? You tilt the telescope, gravity pulls, and it might deform the dish, and you want to avoid that obviously, because if the RMS gets higher, the optical properties get worse. And the question what to do against it. And the first idea people have was, well, we have to make everything stiffer. But that means you need more steel. More steel means more weight. This is perfect for the steel company, but not really for the astronomer. And here people went a completely different path. And that's the reason why it is so rather light. But people here said, and that was the idea actually which went back to Otto von Hachenberg, who was the founding director of our institute, and Sebastian von Hörner, who was also a German astrophysicist located at NRO at that time. And they independently had the idea to say, well, you know the American saying, if you can beat them, join them. So the idea was just, well, don't fight against the gravitational deformation, just use the gravity to deform the telescope, but in a controlled way. And the whole telescope is constructed so that when you tilt it, it automatically deforms from one parabolic shape into another continuously, and just the focal point moves by, when you go from zenith towards the horizon, by 15 centimeters roughly. This is a completely passive system. It's just only construction which makes that happen. It's really was well thought over, and it's working in a way that you always have a very well defined parabolic shape. Well, the deformation is not zero. When I say we have 0.55 millimeter is the RMS, then this is at the best elevation, it's the best value. But it goes to about 0.9 or 1 if you go towards the zenith, but not higher. And it's still good enough to observe down to 3.5 millimeter. And for example, when you look up and you see we have 4 support legs which hold the prime focus. You see where they pass through the dish. There is no connection between the dish itself and the support leg. So the idea is that the dish can deform along the support leg when it's being tilted. And actually the whole construction of the 4 legs, of the support legs, of the prime focus, and the construction of the dish have really no connection. The forces are all end up in this counterweight where we just go. In the elevation, at the elevation drive, and if you look up there, you see the construction which holds the dish, the backup construction, and these support legs. There are no connections, and this is one part of this, one important part of this construction. And well, this was the first telescope which was built following this construction principle. We call it now the principle of homologous deformation.
How come the Sardinian telescope hasn't been designed like that?
Well, nowadays you would put an actuator on each panel. I mean, if you look up, you see the dish consists of individual panels. There's 2,360. In Sardinia, as well as the Green Bank or the FAST telescope, all they have actuators there. That's certainly, well, somewhat more modern. On the other hand, I mean, first of all, that was not possible 50 years ago. Secondly, it means a lot of maintenance effort. I visited the colleagues in Greenbank. They told me after the winter, always 10% of the actuators are not working anymore and have to replace. And third, it might also cause RFI or problems because, well, you need electronics to steer these actuators, and you have to be very, very careful not to interfere with your own observations. So we are quite happy to have this system because it's completely passive and works quite well even after 50 years.
It's quite efficient.
It's efficient. Yeah. It's not as good as actuators, but still, it works very, very well for us.
How many dishes use this system?
Well, I think that, I'm not sure about that. I think also the Pico-Veleta telescope has been built following this homologous deformation. I'm not sure with others, I can't say. As I said, at some point people then started to build actuators on the dish. Or making a combination of both. In front of us, it looks a bit like an American postbox, are the engines. These are 25 kilowatt DC engines, so it's like a very, very small car. But still, 25 times 16 is enough, as you will see later, to accelerate the telescope to quite a good speed. But still, I mentioned that before, more important than the speed, as desirable it is to be faster at your target, more important is the accuracy. And the number, I said already, is about 2 to 3 arc seconds, which we can use, which we can reach during observations if it's not too windy or so. And we reach that by a trick. From the 16 engines, 8 always push the telescope clockwise, 8 put it counterclockwise during an observation, not during the fast slewing. And so they work against each other, and that gives us this very, very high accuracy in positioning. And well, as said, if it's not too windy, not too sunny, we reach these 2 to 3 arc seconds. And just to make clear what that means, because actually I cannot really imagine an angle of 2 arc seconds. The track has a diameter of 64 meters, so we have a 200 meter circumference. And if you calculate that, 2 arc seconds correspond to 0.3 millimeter on the track. And this is the accuracy with which we have to and normally can position the telescope by this trick. 0.3 millimeter with 3,200 tons. One more word on the weight. As I said, 3,200 tons, 32 wheels, so we have 100 tons per wheel lasting on the track. That's therefore, it is specially hardened steel and about 30 centimeters thick. And we have about, in the very early part of the construction, the track was founded with more than 100 concrete pillars, 8 to 12 meters deep, which last on solid rock and hold the telescope stable.
Yeah, it's just a silly question, but since it's raining, I was wondering, is there any chance that it slips by a fraction of 0.3 millimeter, and then that's what?
Nah, well, not really. I mean, we are careful when it's raining, that's true.
Yeah.
And
are you getting slower?
Well, normally the operator makes a slow 90-degree movement to clean the track. And you see there are some, well, I don't know what the proper English term would be, some say devices to push the humidity away.
Oh yeah, right. Yeah. Like,
But actually, this is not enough water. It must be much more, or there must be much more rain that you really have problems. And the worst thing is actually not really the rain. Even worse if, say, we mow the grass and we have some grass on it or so, and then sometimes really one wheel slips.
Yeah.
That gives a very terrible sound. Really, we hate that. So
you need to get out with your broom and like just
something like that. Yeah, sometimes. Yeah.
And this ice problem?
Well, rarely, because well, the pressure is so high, and this things push it away. But if it's really bad, then really somebody cleans it up before we start observing.
Человек, колесико крутится на заднем плане. Так, посмотри, мы вращаемся. Россия. У меня сейчас голова закружится.
Maybe he has the driest spot. Maybe he has the driest spot. Yes.
Secondary mirror, and then use that one to reflect the wave in the center of the main dish, in the secondary focus pattern. And the reason why we do that is because there we have about 7 or 8 receiving systems between which we can switch within 30 seconds, and it gives us quite some frequency agility. For example, interesting, we run a number of programs where we observe AGNs and their variability, and we can get the whole SED, the whole spectral energy distribution, from 2 to 50 gigahertz within half an hour or so by just switching quickly between these two things. And well, the old subreflector, I mean, this was replaced in 2006, and we just kept the old one there. It's a 6.5 meter diameter elliptical mirror, so with 2 focal points. And if you will later look up in the prime focus, as I said, you can do it well from the visitors pavilion if you stop there on the way home. You will see how small that looks, and to have a good scale, we kept this here. So this is how big it is. Which we use for, say, education purposes, internships.
Сходим по вращающейся лестнице. Красивее.
plus minus 270 degrees around west. West is roughly where the stairs are. But it turned out that this is already too much, so that the cables would twist too much, and we can go for plus minus 240 degrees. So we have 1 1/3 of a full circle. And if you get close to the end switch, you have to really go back 360 degrees. So it means you have to do some proper observation planning not to waste time. I mean, as I said, 15 minutes is, well, the telescope can be quite fast, but 15 minutes for a full circle is 15 minutes, and you want to avoid that, obviously. If you look outside, from the outside again, there's this cable twist. There is really, you can see it's a kind of a pipe or a tower, a few meters high. I think in total from here it's 10 meters or so. So it's really a very long way for the cable to twist. These devices are there to hold them stable, and the weights are there, not that it's not lifted up by turning. And well, as I said, you get plus minus 240 degrees this way. In the center is the angular measurement, the angular recorders for getting the exact position and reporting them to the control system. Many things are changing at the moment. I mean, in the old days we had, as other telescope, lots of coax cables to get the signal from here up into the control building. Now we are in a process of digitizing the receiver signals already in the receiver, and which sounds easier than it is. I mean, because it's not difficult as such, but it needs or could lead to much interference, and we obviously try to avoid that. So it means we have to do some proper shielding, and but that will be in future. We will have all receivers having the signal digitized already in the cabin, and that makes things much easier. Obviously, just transporting wire and a network line. We have no problems with distance, no problem with phase jumps anymore by cables tilting and everything. And you can get this broadband signal in our computer room in the Faraday cage, and from there it will be handled then by proper backends, which are nowadays rather computer clusters, so that you can really analyze the data in any fashion you want. In the old times you had, now still you had specific backends for either continuous spectroscopy or parts of it, and then it's much easier with the new system to do everything at the same time if you want. There was actually one question down here, a good question about the snow in the telescope and the heavy load. We try to avoid that we collect snow, and it starts snowing, the operator brings the telescope in a protected position. This is normally looking towards the horizon, in the best case with the backside to the wind, so that we don't collect snow in the dish. The reason is just its weight, its additional weight. We have 9,000 square meters. Is the area of the dish, and 1 centimeter of wet snow will give you many tons additional weight, and you just want to avoid that. I mean, this is mostly danger for the engines for the years. A number of years ago, I cannot remember when that was, we had winters. Nowadays we don't have any winter here anymore. It's maybe getting a bit cooler, but we used to have much more snow 20 years ago or so. And I remember one occasion where, despite the operator driving the telescope in the protected position, we collected so much snow in the lower part of the dish, which was just blown in by the wind at the edge, that you couldn't switch on the telescope anymore. I mean, there was so much additional weight on the engines that they automatically switched off. And then it took 2 colleagues of us 2 or 3 days, and they used a big water pipe to wash the snow out of the dish in the lower part, and we could switch it on again and run the telescope again. But as I said, this kind of winter we don't have anymore, unfortunately. The observer takes over. I just want to show that because this is our ultra broadband receiver. It's a receiver which covers frequency from 1.3 to 2.6 and 3 to 6 gigahertz instantaneously. Well, you can see the spectrum here. This is now the lower part only, and you see we put some window here to get a proper signal. It would be much different if we go to here or another place. Most of what you see here is interference. That's really the problem nowadays. It's minimal. Really big problems with this emitter here. This is an LTE equipped emitter by Deutsche Telekom, which is located 2 or 3 kilometers from here. And that was so broad that it really brought the receiver into saturation, at least the 21 centimeter, the old one. Unfortunately, we could negotiate with them, and they were turning down their power and also give it a tilt, so that we now can't live with that anymore. I mean, it's a perfectly legal system, no doubt. This is their band, but it was so strong that it completely saturated the receiver. Very massive, and it's shielded, so it should have an attenuation of about 100 dB. And this is about 20 years old, and we decided to build this and to bring every fast computer and every say hardware which is potentially causing problems, EFV problems, RMI problems in here. And so now we have all the computers which control the telescope here, so we have the backends here, and there are also this new computer cluster which will be used especially for pulsar observations is all located here. Apart from that, a number of servers from the Bonn IT are mirrored here, as well as our data archive. So we have it in 2 different sites and 2 different locations. In case something really bad happens, we have some backup.
What about the computers that are outside in the control room? Do they need to have
this is so-called FM200, as you see here. In principle, it's supposed to survive it, but it's obviously not very healthy, and but in any case, if there's a fire, you should better get out. Okay. But theoretically, it's supposed to that you can survive it when you are inside, instead of carbon dioxide, which you won't survive.
Is this sign
Just don't sit inside, they say.